Tonight, we're going to explore one of the most overlooked truths in all of modern science. Look up on a clear night and the sky seems full of light. Thousands of stars, each one a sun, many of them far larger and brighter than our own, burning across the dark. Stars are among the brightest objects that exist anywhere. And that is the strange part. So why is the space between them so completely, so utterly black? It sounds like a simple question. It is not. The answer reaches down into the physics of light itself, into the limits of the human eye, and into a paradox that quietly troubled astronomers for 200 years. Because here is the first unsettling thing you need to know. The darkness you picture when you imagine dark is not the real thing. You have never seen the real thing. Almost no human ever has. In 1984, an astronaut named Bruce McCandless did something no person had ever done before. He drifted away from his shuttle with nothing connecting him to anything. No tether, no handhold, nothing between his body and the open void. And when he turned away from the Earth, away from the sun, and looked into deep space, he saw something. Or rather, he failed to see something that he would struggle for the rest of his life to put into words. That is the darkness this video is about. Not the dark of a room with the light switched off. Not a moonless night, far from any city. Something categorically different. A darkness that can surround a sky full of blazing stars and still swallow them whole. By the end of tonight, you're going to understand why a universe overflowing with light is still overwhelmingly dark. Why the stars you see are the rare exception and not the rule. Why your eyes can detect a single particle of light and yet register absolutely nothing in the depths of space. And what this darkness reveals about our perception, our evolution, and our future among the stars. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Think about the last time you turned off every light in the room. The moment the switch clicked, it felt dark. Maybe completely dark. Maybe the kind of dark where you waited a few seconds, half expecting your eyes to adjust, and then decided the room was as black as a room could get. It wasn't. Even in that room, light was reaching your eyes. A thin line of orange under the door, the faint blue pulse of a charging indicator on the far wall, the diffuse glow leaking around the curtains from a street lamp 3 houses down. None of it felt like light. But the eye doesn't measure light the way a physicist does. It adapts. Here's what actually happens in the dark. When the lights go out, your pupils widen to let in more of whatever is available. Deeper in the eye, your rod cells, the photoreceptors specialized for low light vision, begin a slow chemical transition. They are not instantly sensitive. They need time. After roughly 20 minutes, they reach their maximum sensitivity, and at that point the eye becomes extraordinarily good at detecting faint sources. Not extraordinarily good at detecting nothing, good at detecting the faint. And on Earth, faint is not nothing. A full moon delivers enough light to cast a shadow. Starlight contributes thousands of individual photons to your retina on a clear night. The Milky Way band, even where it seems like a dim smear, is a structured glow. The atmosphere itself emits a faint, permanent light called airglow, the result of chemical reactions in the upper layers of air. Solar system dust catches sunlight and scatters it back as zodiacal light, a soft pale cone rising from the horizon after sunset and before sunrise. And above all of this, scattered by the atmosphere from cities hundreds of miles away, urban light pollution climbs into the sky and reflects down again. You cannot see the source, you can still feel the effect. The atmosphere is not transparent to light the way a vacuum is. It bounces light around, it holds it. On the night side of Earth, you are still bathed in reflected sunlight, moonlight, starlight, air glow, and scattered city glow, all simultaneously, all the time. On Earth, you have never stood in true darkness. Not once. But here's where it gets strange. You could already suspect this. You could already nod and say yes. Technically, there is always some photon reaching my eye. Technically, the room is not perfectly dark. And that seems like a minor technical point. a distinction that doesn't matter much. Just physics being pedantic. It isn't. The difference between the darkness you know and the darkness that exists outside Earth's atmosphere is not a small gap. It is not the difference between dim and dimmer. The darkness in open space is a different category of experience entirely. Not the absence of bright light. The absence of light at any scale your biology is equipped to process. Astronauts report this consistently. When they travel beyond the atmosphere, when Earth is behind them and the sun is behind them and they turn to face open space, what they describe is not what they expected. They expected stars against black. Stars against black is what you see from the ground on a clear night. A rich field of points of light, bright ones and dim ones, a dense belt of them along the galactic plane, and behind all of it, a dark background. That is the picture. That is what the mind constructs. What they actually see is different. The stars are there, but the space between them, the gaps between the points of light, is something the eye cannot negotiate with. It has no texture, no variation, no gradient, no depth cue, nothing for the brain to hold on to. And the brain, which is built to extract information from whatever is presented to it, receives from that darkness no information at all. In 1984, Bruce McCandless became the first astronaut to perform an untethered spacewalk, drifting free of the shuttle with no line connecting him to anything, no crew member within reach, nothing between himself and open space. When he turned away from Earth, away from the sun, and looked into the deep void, he described a darkness so complete it felt almost physical, not surrounding, penetrating. He held his hand away from any reflected light and could not see it. Not as a dim shape, not as a silhouette, nothing. His hand was there. He knew it was there. His eyes returned nothing. Other astronauts have reported the same thing. The psychological response is hard to articulate. The brain expects something. It is built to expect something. Evolution did not produce a nervous system prepared for absolute sensory withdrawal on this particular channel. When the eye opens wide and receives nothing, the brain does not interpret this calmly as an absence. It reaches. It searches. It tries to construct an image from what should be there, and it finds no signal to work with. That is the darkness this script is about. Not the dark of a room with the lights off. Not the dark of a moonless country night. The dark of the gaps between stars. The dark the universe is mostly made of. You have a reference point for what darkness feels like. That reference point is wrong. And what it is wrong about turns out to matter considerably, because the story of why the universe is so dark and what that darkness means is only beginning. What was really happening to his eyes out there is worth asking plainly, because the darkness McCandless encountered was not simply darkness taken to an extreme. It was something categorically different. And to understand why, you have to start with what space actually is. Space is almost perfectly empty. Not empty in the way a quiet room is empty. Not empty in the way a clear sky looks empty. Empty in a way that has almost no comparison in ordinary life. In interstellar space, the density of matter is roughly 1 atom per cubic centimeter. 1 atom. In the volume of a sugar cube. That is the average. Not a particularly sparse region. The average. Now consider what that same volume contains on Earth. A cubic centimeter of the air around you holds approximately 27 followed by 18 zeros worth of atoms. 27 billion atoms in a sugar cube's worth of air. Against 1. That gap is not a difference of degree. It is a difference so vast the comparison barely holds together. Engineers on Earth build vacuum chambers to study conditions close to empty space. The best vacuum chambers ever constructed still contain billions of atoms per cubic centimeter. Still incomparably denser than the space between stars. The emptiness of interstellar space is more extreme than anything human technology has ever achieved in a laboratory. We cannot even manufacture it. And that emptiness is the reason the universe is dark. Here is the physical principle. Light does not need matter to travel. A photon crosses the solar system at 186,000 miles per second and requires nothing from the space it crosses. It does not interact with what is not there, but light also cannot be seen unless it hits something. Your eye, a surface, a dust grain, some physical thing that absorbs or scatters the photon and turns its energy into a signal your nervous system can process. Without that collision, the photon is invisible, completely. It passes through your exact location and leaves no trace. You feel nothing. You see nothing. There is no glow, no shimmer, no suggestion that light is present at all. This is the part that resists intuition. On Earth, you can watch a shaft of light cut through a dusty room. You see the beam itself. You see the column of light as a visible object. But you're not actually seeing the light. You're seeing the dust. You are seeing the air molecules. You are seeing all the tiny particles scattering photons sideways toward your eye. The beam is visible because the room is full of matter too small to notice but too numerous to miss. Remove the dust, remove the air, and the beam disappears. Not because the light is gone, because there is nothing to scatter it toward you. In space, there is nothing to scatter it. Space is saturated with photons, light from billions of stars, light from ancient galaxies, the faint remnant glow of the early universe itself, all of it streaming through the void continuously. If you floated in interstellar space, photons would be passing through your body from every direction, and you would see none of them. Not a glow, not a haze, nothing. Because they are traveling through you, not toward the structures in your eye that register their arrival. The darkness is not evidence that light is absent. The darkness is evidence that there is nothing for the light to strike. Think about what that means for a spacecraft far from any star, not in our solar system, where the sun still dominates. Out past the edge of it, in the void between stellar systems. You look out a window aimed away from the stars. What you see is pure black. No shade of grey, no texture, no depth, no gradient from slightly darker to slightly less dark. The visual field in that direction is a complete absence of signal. Your eyes evolved over hundreds of millions of years to detect faint light. They are extraordinarily good at it. In complete darkness, they will dilate fully and activate every rod cell available, pulling in whatever photons exist. But they evolved on a planet where some photon is almost always present. They did not evolve for a condition where the input is literally zero. With no photons arriving, the visual cortex has no data. Not degraded data. No data. You raise your hand in front of your face. You wave it slowly. You can feel the air move, feel the slight shift in temperature, feel the presence of your own skin. But there is no visual indication of movement at all. Not a shadow. Not a shape. Not the suggestion of something passing. Nothing. The hand is there. The light that could reveal it is somewhere. But the light is not hitting the hand. And the light that is hitting the hand is not reaching your eye, and so the hand is invisible. You are, in that direction, effectively blind. Seeing becomes a meaningless concept. This is the reality of most of space, not a canvas hung with stars. A near infinite darkness with occasional islands of light separated by distances that take light itself years, decades, centuries to cross. The stars are the exceptions. The dark is the rule. Something else was happening. This darkness operates at scales we can observe right here, within human reach. Astronauts working outside the International Space Station describe an experience that makes the principle concrete in a way that is hard to forget. On the sunlit side of the spacecraft, surfaces reach temperatures around 250 degrees Fahrenheit, roughly 120 degrees Celsius. The metal and thermal blankets are not merely warm, they are baking in direct, unfiltered solar radiation with no atmosphere to soften it. The light is not scattered or dimmed on its way in. It hits directly and hard. Step around to the shadowed side, separated from sunlight by a distance of perhaps a few feet of spacecraft wall, and the surface temperature drops to roughly negative 250 degrees Fahrenheit, approximately negative 157 degrees Celsius, a difference of 500 degrees Fahrenheit across a gap you could step over. Because there is no atmosphere to carry heat from one side to the other, no air to spread warmth around a corner, and no scattered light to gently fill the shadow. On Earth, shadows are incomplete, light bends around edges, air molecules scatter photons into spaces the direct beam does not reach. A shaded surface is cooler and dimmer but still visible. Still lit from the side, still touched by the general diffuse brightness of the sky. In space, shadow means something absolute. The sunlit surface is blindingly bright. So bright that looking at it without eye protection would cause immediate damage. The shadowed surface, a hand's width away, is completely invisible. No fill light, no ambient glow, nothing. Astronauts have reported this with a consistency that suggests it never becomes ordinary. A glove, a tool, a handrail passing from light into shadow does not dim. It does not fade. It vanishes. Still felt in the hand. Still gripped. Still physically present. But visually gone. Simply gone. That is what space does to light. That is what emptiness does to visibility. And that is only the beginning of what the darkness means. Pull back now from that single hole, that single edge where light ends and darkness begins, and scale up by a factor that the mind resists. Not from one side of a spacecraft to another, from one star to the next. Stand on Earth on the darkest night you can find. Travel far from cities. Find a high desert plateau or a remote ocean island. Wait for your eyes to fully adjust. You will see perhaps 5,000 stars. That is the limit of what the naked eye can resolve under ideal conditions. 5,000 points of light scattered across the dome of sky. They feel numerous. They feel close. They feel like company. That feeling is wrong. Each one of those points is separated from its neighbors by distances so vast, the numbers take a moment to settle. Proxima Centauri, the nearest star to our sun, sits about 424 light years away. That means it takes light traveling at 186,000 miles per second, more than 4 years to make the crossing. In miles, that distance is roughly 25 trillion. In kilometers, roughly 40 trillion. 25 trillion miles to the nearest star. Not to a distant galaxy, not to the edge of the universe, to the neighbor. Think about what that means in human terms. Every spacecraft we have ever launched moves at speeds that seem enormous from the surface of Earth. But at those speeds, a journey to Proxima Centauri would take tens of thousands of years. We have never sent anything even a fraction of that distance. Proxima Centauri is not reachable in any practical sense we currently possess, and it is the closest one. In our region of the Milky Way, the average distance between stars runs about 5 light years, not clustered together like cities on a map. Scattered. Here is one way to feel that spacing. Imagine taking a small handful of grains of sand and spreading them so that each grain sits roughly 4 miles from the next. 4 miles of empty air between each tiny grain. From any single grain, the others are invisible to the naked eye. The space between them is not a gap. It is the dominant reality. The grains are the exception. The space is the rule. That is what the galaxy actually looks like from inside. But knowing the number is different from standing in it. So imagine you could be placed exactly halfway between our sun and its nearest neighbor, 2.5 light years from each. At that distance, the sun is no longer a disk. It is a point of light. Bright, certainly. Brighter than any other star in the sky. But it illuminates nothing around you. No cast shadows, no ambient glow extending from its direction. No softening of the darkness nearby. A point. A bright point in a sea of other points. And all the other stars, every one of them, also points. Unchanging, steady, cold. Here is what that means for the space you are standing in. There is no light reaching the empty volume around you, not arriving too faintly to see, not traveling in directions you cannot look, simply not interacting with the space itself, because there is almost nothing in that space to interact with. The photons from the sun and from every other star are crossing that volume in every direction, but the volume contains so little matter that the photons pass through it without encountering anything to scatter from. You would not see beams, you would not see glow, you would not see the light in transit at all. You already know why. You covered this. Light requires matter to become visible, and in that halfway point between two stars, matter is essentially absent. In every direction, darkness extending trillions of miles, before reaching anything solid enough to reflect a photon toward your eye. No up and no down, no ground, No horizon, no surface, no scale reference, just floating. Human beings did not evolve for this. Every sensory system you carry was shaped over millions of years on a planet with surfaces and gravity and reflected light, and a clear difference between the ground beneath your feet and the sky above your head. You always know where you are in relation to something. There is always a reference point. A wall, a floor, a horizon, a shadow cast by the sun, telling you where the sun is without looking at it. Your sense of position and scale depends on those references the way your lungs depend on air. Remove them and the brain does not simply adapt and recalibrate. It reaches for something to hold. Astronauts have described this, not from interstellar space, which no human has ever reached, but from low Earth orbit, in the moments when they turn away from the spacecraft and face the open void. The feeling is not peaceful emptiness. It is something closer to the sensation of all reference dissolving. Some have described a sudden, involuntary need to reorient, to find the spacecraft again, to anchor vision to something solid. The void does not fill, it does not recede, it remains, extended in every direction without differentiation, pressing toward you while being nothing at all. And that is while looking out from a vehicle only a few hundred miles above the surface of a living planet. The nearest city is closer than the distance a commercial jet crosses in a single hour. Now extend that into interstellar space. No planet behind you, no spacecraft hull. 2.5 light years of vacuum in the direction of the sun. 2.5 light years of vacuum in the direction of the next star. In every other direction, something similar or worse. The night sky looks populated because we see it from the surface of an exception. A dense, warm, lit object, surrounded by gas and magnetic fields, hurtling through a galaxy we can only see from inside. What the sky looks like from here is not what space is actually like out there. The crowded feeling when you look up on a clear night is an illusion. It is the brain projecting depth cues it was never given. The stars appear to form a canopy, something vaulted and nearby, because the eye has no mechanism for registering emptiness on a scale of trillions of miles. The gaps between those 5,000 visible stars are not small. They are almost incomprehensibly large. And behind them, the gaps between the stars you cannot see are larger still. The darkness is not the backdrop. The darkness is the content. The stars are the rare exception. The void between them is the dominant fact of the universe's volume. And the stars themselves, it turns out, are not the whole story. Go further still. Past the last star of the Milky Way's outer edge, past the trailing wisps of gas and scattered dwarf stars that mark the galaxy's uncertain border, and into the space between galaxies. The darkness you encountered between stars was one thing. This is something else entirely. The Milky Way and the Andromeda Galaxy are our nearest large neighbors. The distance between them is approximately 2.5 million light-years. In miles, that is roughly 15 quintillion miles. 15 followed by 18 zeros. The grain of sand analogy from the space between stars no longer applies here. There is no grain fine enough, no desert wide enough to carry the scale. You are in a different order of emptiness. Between stars, the average density of matter is about 1 atom per cubic centimeter. That number, introduced earlier, already felt incomprehensible. The answer was stranger than expected. Between galaxies, the density drops again. Not by a small factor, by roughly 1 million times. In intergalactic space, there is approximately 1 atom per cubic meter. 1 atom in a volume the size of a large refrigerator. A refrigerator-sized region of space, and somewhere inside it, a single particle of hydrogen drifting alone. That is the average content of the universe's largest volumes. Now, imagine a spacecraft. Not near Earth, not near the Sun, not somewhere in the middle of the Milky Way. Halfway between the Milky Way and Andromeda. Roughly 1.25 million light-years from either galaxy. You look in every direction. What do you see? 2 faint spiral smudges. One behind you, one ahead. That is all. 2 pale, dim, ghostly patches of light that do not resolve into individual stars no matter how long you look. Every other galaxy, in every other direction, is millions of light years beyond those 2. reduced to faint smudges even through the most powerful telescope you could carry. The nearest anything is more than 1,000,000 light years away. The void surrounding you is not empty in the way interstellar space is empty. It is empty in a way that has no useful comparison in human experience. Now look more carefully at those two smudges. One of them is the Milky Way. Inside it, somewhere, is the Sun. Not visible, not identifiable as a single point of light from this distance. The Sun has dissolved into the general glow of the galaxy, contributing its fraction to the faint blur you are looking at. Everything that has ever happened on Earth, every city, every war, every life, every conversation, is contained inside that barely perceptible smear of light. All of human history, all of human civilization, compressed into a dim patch that you could cover with your thumbnail held at arm's length. Not as a metaphor, as a literal geometric fact. This is the scale at which the universe operates. The darkness between those two smudges is not incidental. It is not a gap to be crossed and left behind. It is the majority of the universe's volume. It is the dominant fact. And here is the question that has followed astronomers for centuries. If the universe is full of light, why is the sky dark at all? Think about that seriously. Not the darkness between galaxies, but the darkness of the night sky as seen from Earth. Stars exist in every direction. Billions of galaxies spread across the observable universe, each containing hundreds of billions of stars. Quasars blazing with more energy than entire galaxies. The cosmos is saturated with light sources. So why, when you step outside on a clear night and look up, is the sky black between the stars? This question has a name: Olbers' paradox. It was articulated in detail in the early 19th century, though thinkers had wrestled with it for much longer. The logic is straightforward. If the universe is infinite and uniformly filled with stars, then every single line of sight from your eye, in any direction you point, should eventually terminate on the surface of a star. Not a distant star dimmed by distance to near invisibility. An actual stellar surface. Because in an infinite, uniformly populated universe, there is always another star along every line of sight. No matter how far you look, the sky should blaze. Every point of the night sky should glow as bright as the surface of the sun. The entire dome of the sky should be brilliant, not dark. The night sky is not brilliant. It is dark. Something is wrong with the logic. But what? The answer comes in two parts, and each part reveals something fundamental about the universe itself. The first part: the universe is not infinitely old. It has a finite age, approximately 13.8 billion years. Light travels at about 186,000 miles per second. That speed is fast, but it is not instantaneous. Light from an object 13.8 billion light years away has taken 13.8 billion years to reach us. Light from an object farther than that simply has not had time to arrive. Not because nothing exists beyond that distance, but because the universe has only been around for 13.8 billion years. The observable universe, the sphere of space from which light has had time to reach us, extends roughly 13.8 billion light years in every direction. Beyond that boundary, light is still traveling toward us. It has not arrived yet. Those stars exist, but we cannot see them. The lines of sight that should terminate on a stellar surface instead reach into distances from which no light has yet had time to travel. Not all the sky is filled, not because the universe lacks stars, because the universe lacks age. The second part: the universe is expanding. The galaxies beyond our local group are receding. Not moving through space in the conventional sense, but carried apart as space itself stretches. The light from those receding galaxies is stretched too. Wavelengths that began as visible light are pulled toward longer and longer wavelengths as they travel across the expanding universe. This stretching is called redshift. The most distant galaxies we can detect in any way have their light shifted so far that it has left the visible spectrum entirely. It arrives as infrared radiation or as microwaves. Our eyes cannot perceive it. The light is real. It reaches us. But it is invisible to human vision. Shifted into wavelengths our biology was never built to register. Those galaxies still exist. Their light still travels. but our eyes cannot see it. Put the two parts together. The darkness of the night sky is not a puzzle or an oversight. It is a direct consequence of what the universe is. Finite in age, so light from the most distant reaches has not arrived. Expanding, so light that has arrived has been stretched beyond visibility. The darkness is written into the structure of the universe itself, not a failure of light, a consequence of time and growth. A dark sky means you live in a young universe, still expanding, still sending light toward you that has not yet come. The universe does not look full, but the fullness is there. Most of it is simply invisible, arriving too late or arriving in wavelengths your eyes were never made to read. What you see on a clear night, those few thousand stars against the black, is not the universe. It is a narrow slice of the universe, filtered by the limits of human sight and the finite age of everything. The darkness between those stars is telling you something. It is telling you that the universe is growing, that it had a beginning, that it is not yet done. The night sky is dark because the cosmos is still in the process of becoming what it will eventually be. And what it will eventually be, even now, is beyond what any eye will ever fully see. All of that, every piece of it, was built by a universe that cannot fully see itself. The eye that tries to read the night sky is the same eye that evolved in firelight, in shade, in the quick shadows of a world that was always, at some level, lit. Let's come back to that eye. Let's think about what it actually was built for. Under ideal conditions, the human eye is extraordinary. Adapted to full darkness for 20 minutes, the rods active and primed, a person can detect as few as around 100 photons entering the pupil. Some research suggests single photon detection may be possible under the right conditions. 1 photon, a single packet of light. That level of sensitivity is not engineering. It is biology refined over millions of years in environments where finding even the faintest trace of light could mean the difference between living and not. But here is the catch. That sensitivity is only remarkable when there are photons to detect. In true space darkness, there are none. Not fewer than you are used to. Not a trickle too faint to register consciously. 0. The machinery works perfectly. There is simply nothing to trigger it. Think about what that means at the level of the instrument itself. The most sensitive light-detecting organ in the known world, pressed against a darkness where nothing arrives. Not malfunctioning. Not strained beyond its limits, just waiting, endlessly, for input that does not come. That situation is stranger than it sounds, and it becomes stranger still when you consider how dark the objects out there actually are. Many asteroids reflect only 3 to 5% of the sunlight that strikes them. 3 to 5%. That is darker than coal, darker than fresh asphalt on a summer road. If you flew close to a large asteroid and approached it from the side facing away from the sun, you would be approaching a black object against a black background. Not a dim shape, not a silhouette with some faint definition, a negative space. You would know it was there only because the stars behind it were gone, replaced by nothing, and only careful observation or computer-assisted processing would reveal any structure at all. Step onto that asteroid's sunlit face, and the scene changes. The terrain is exposed, harshly lit, every rock throwing a razor shadow. But look into any crater. Look into any crevice. Look anywhere the direct line of sight to the sun is broken. The shadow is absolute. Not dim, not deep. Absolute. The eye finds no photons there because no photons are there. The darkness inside a sunlit asteroid crater is the same darkness as the space between galaxies. And on the asteroid's night side, with the sun behind the horizon, the millions of stars spread across the sky provide nothing useful. You might expect all that starlight combined to offer some illumination. It does not. Artificial light is required for basic tasks. Without it, you cannot see your own hand at arm's length. But go further in. Go inside. An earthly cave feels dark, and in many conditions it is nearly dark, but not truly dark. Even in the deepest cave, your body is producing something. Bioluminescence is a real, measurable byproduct of metabolism. Cells emit ultra-weak light as a consequence of chemical reactions happening continuously inside you. The amount is vanishingly small, far below what the eye can consciously detect, but it exists. The darkness of a deep cave is, in the strictest physical sense, not quite total. Inside a hollow cavity in an asteroid, it is. No external light penetrates. No sunlight. No starlight. No scattered photons working their way through rock. No biological source from other organisms, because there are none. No chemical source. No atmospheric chemistry. Nothing. The darkness is complete in a way that no natural place on Earth can match. Your eyes would strain, not because they are damaged, because straining is what eyes do when the signal falls below threshold. They search, they amplify, they reach for gradations that are not present, and they find nothing. No vague shape in the dark, no subtle difference between near and far, no suggestion of a surface a foot in front of your face, nothing. Here is where it gets strange. Sensory deprivation research has shown that when the brain is starved of visual input for long enough, it begins to generate its own. Geometric patterns at first, then more complex imagery. The brain, wired to receive and interpret an unceasing flow of visual data, does not simply go quiet when the data stops. It fills the silence. In total darkness, in a place where there is genuinely nothing to see, the eye would eventually be reporting images that are not there. The darkness creates its own hallucinations. That finding matters because roughly 30% of the human brain is devoted to processing visual information, more than any other sense. Vision is not one tool among many for navigating the world. It is the primary architecture. Everything else, hearing, balance, temperature, touch, sits alongside it. But vision is the lead. Take it away and the brain does not gracefully redistribute the load. It panics quietly. On Earth, that panic is manageable. Even a person who is completely blind still receives cues from sound bouncing off walls, from air currents indicating open space or obstacles, from temperature changes that carry information about the environment. In vacuum, those channels close. Sound does not propagate. There is no air to feel. Temperature does not correlate with nearby objects because there are no nearby objects close enough to matter. The only sensory input left is proprioception, knowing where your limbs are relative to each other. But proprioception gives you no reference to anything outside your own body. You are a nervous system floating in a void, with no data coming in from beyond your own skin. This is why the fear is not theoretical. Throughout human history, darkness meant something. It meant that predators could see you, and you could not see them. It meant that you could not see where to step, what was in reach, who was coming. Ancestors who feared the dark and sought fire and shelter and enclosed space survived in greater numbers than those who did not. That preference was passed on, refined, embedded. Children fear the dark not because they are taught to, but because the fear is already there, written into the architecture, waiting to activate. Horror uses darkness not as a convention, but because it reaches something fundamental. Even in a room you know to be safe, complete darkness can elevate the heart rate before any rational thought intervenes. The response bypasses reasoning because it was built before reasoning existed. In space, that ancient response meets a darkness it was never designed to encounter. Not the darkness of predators, the darkness of absence. Nothing is hiding in the shadows out there. Nothing is waiting. Nothing is watching. Because there is nothing. No life, no movement, no sound if you could somehow hear it. No air, no warmth from any source. The threat that the fear was built to flag does not exist here. But the fear fires anyway, because fear does not check. It responds to total darkness regardless of what the total darkness contains. Some astronauts have described a specific moment during spacewalks, when facing open space in deep shadow, when the intellectual understanding of their situation collapsed into something visceral. The darkness extends in every direction forever. Not metaphorically forever, physically forever, or as close to forever as the observable universe allows. Earth and everyone they know, and every city and every conflict, and every piece of history is behind them. One tiny lit point, not even visible from most of the universe, surrounded by this. The sense of insignificance stops being an idea and becomes a bodily sensation. And here is where the response splits. Some find it liberating. If you are cosmically small, if humanity is a brief flicker on one ordinary planet among hundreds of billions of others in one ordinary galaxy among hundreds of billions of others, then the weight of daily life, its urgencies and anxieties and grievances, does not actually carry the significance it seemed to carry. The darkness puts things in proportion. Seen from out there, the things that fill a human day with tension are microscopic. That is not nothing. That is a kind of relief. Others find it crushing. Not as a theory, but as a felt reality. Nothing we have built will matter at this scale. The empires and the art and the languages and the loves are happening on a barely visible speck in an uncaring void that stretches beyond our ability to comprehend it. There is no one watching. There is no reference frame from which our existence registers as significant. The darkness does not even register our presence. It was here before us. It will be here after. And it does not care. Both responses are valid. They are two different ways of processing the same fact, which is that we are temporary, local, small, and the universe is vast, old, and indifferent. Darkness is dominant, light is the rare exception. And the eye built to find that light, the one staring up on a clear night at a few thousand stars, was built for a world where there was always something to see. That eye has never fully negotiated with what it is looking into. Now imagine having to live inside that feeling, not for a moment of awe at the edge of a spacewalk, for months. That is the reality facing every crew that will travel to Mars with current technology. The transit alone takes somewhere between 6 and 9 months. 6 to 9 months of sealed habitat, recycled air, and the same small faces across a table the size of a van interior. And outside every window, the same thing. Darkness broken only by motionless, unchanging stars. The journey begins with something almost comforting. In the first weeks, Earth is still visible. A blue marble, small but recognizable. You can see the curve of continents. You can see weather. Then it shrinks. Blue marble becomes a blue dot. Blue dot becomes a point of light among other points, indistinguishable at a glance from a bright star. And then even that fades. Earth does not set like a sun. It does not fade gradually like a light being dimmed from the other room. It simply becomes too small to carry meaning. The most significant object in the history of every human who has ever lived recedes to nothing in a matter of weeks. Mars is no comfort. For most of the transit, Mars is also a point, a reddish dot that brightens, slowly, over months. There is no approaching a destination in any visual sense you would recognize. There is only the slow reddening of one particular star among thousands. The spacecraft is the world, not a metaphor, literally the world. But the reality was different. On the International Space Station, isolation has a ceiling. Astronauts orbit at roughly 250 miles up. The planet fills the windows. Weather systems scroll beneath you. City lights emerge at night over continents you can name. You are isolated from the surface, but the planet is right there. It is an anchor, something to look at, something that is home. Mars-bound crews lose that anchor entirely. Earth vanishes, and as it vanishes, so does real-time contact with it. At maximum separation between Earth and Mars, a signal traveling at the speed of light takes up to 20 minutes to arrive. One way. Not 20 minutes round trip. 20 minutes each direction. You cannot have a conversation. You cannot call for help and wait for an answer in any useful time frame. If something goes wrong, you send a message and wait 40 minutes for a response, during which the situation has either resolved itself or destroyed you. A small crew in a small spacecraft, surrounded by darkness extending hundreds of millions of miles in every direction, with the nearest possible help months away in travel time. No real-time voice, no real-time anything. Think about what that isolation means at the psychological level. The analogy that comes closest is a lifeboat in the middle of an ocean so wide, there is no horizon in any direction. Not a distant shore somewhere. No direction that is toward anything. Open water in every direction with no end and no reference. Even that analogy breaks down eventually, because at least in a lifeboat there is weather. There is the feel of wind and the sound of water and the temperature of air on skin. Mars crews have none of those external inputs. The darkness outside is absolute and completely silent. Mission planners know this. The psychological support architecture built into Mars transit designs is substantial. Scheduled communication windows with Earth exist even when the delay renders conversation impossible, because the act of sending and receiving a message, however slow, maintains a thread of connection. Entertainment systems carry movies, music, libraries of books. Interior lighting in mission designs is adjustable, cycling through simulated day and night to keep the circadian rhythm from dissolving. Without that rhythm, sleep degrades. Without sleep, decision-making degrades. Without decision-making, the mission ends. Windows are a design question with no clean answer. The instinct is to maximize them. Natural light, visual variety, a sense of the outside. But the outside, in this case, is unchanging darkness. Studies of long-duration simulated isolation suggest that some crew members become fixated on the darkness in ways that deepen rather than relieve distress. Covering windows or limiting their size is not deprivation. It may be protection. Mission designers still debate where the line is. The consensus is that any visual input, color on walls, rotating art selections, the simple engineering choice of making some surfaces yellow rather than grey, matters more than common sense would suggest. But here is where the selection question becomes the hardest problem. You can design the lighting, you can schedule the communications. You cannot engineer away the fact that some people handle prolonged isolation better than others, and the differences are not random. Crew selection for Mars missions screens specifically for psychological resilience under isolation. Can this person maintain functional morale when they are effectively cut off from social contact? Can they tolerate the unchanging darkness outside without it consuming their attention? Can they resolve interpersonal conflict inside a tiny vessel when there is no escape, no walk around the block, no space from the other person until the mission ends? These are not soft questions. Mission failure has come from psychological breakdown as readily as from technical failure in long-duration isolation studies on Earth. Cultural composition adds another layer. Research on personality and isolation suggests that individuals from cultures that place high value on personal independence, the cultural orientation sometimes described as individualist, may tolerate isolation with fewer acute stress responses than individuals from cultures that center collective identity and constant social connection. Neither orientation is superior. Both contribute strengths. But a crew assembled without awareness of these dynamics can produce a group in which some members are carrying disproportionate psychological weight, while others are not equipped to recognize the load they are generating. International crews need cross-cultural composition planning. The goal is not homogeneity. The goal is complementary coverage, so each member's stress profile is balanced by another's resilience. And then there is what the darkness itself does to the brain, beyond the psychological stress of isolation. In studies of people placed in continuous darkness environments, brain scans reveal something that looks at first like a malfunction. The visual cortex does not go quiet when deprived of input. It does not simply wait. Within days, it begins responding to other senses. Sound activates regions that normally process sight. Touch activates visual areas. The brain is redistributing its processing budget, reassigning the enormous computational resources normally devoted to vision toward inputs that are still arriving. This is called cross-modal plasticity. It is the brain adapting to a changed sensory world. Spacecraft interior lighting prevents this in current missions. The visual system stays active, stays calibrated. But extended exposure to true and continuous darkness, the kind that cannot be fully simulated on Earth, could trigger the same reorganization. And reorganization has consequences. A brain that has rewired its visual processing to handle touch and sound more efficiently is not the same instrument it was at launch. Readaptation on return may be difficult. The degree to which this applies to months in a vessel lit only artificially while surrounded by absolute darkness outside is something we do not yet fully know. We have proxies. We have short duration studies. We have isolation simulations on Earth and in orbit. But the specific experience of 9 months in transit with darkness extending in every direction and Earth reduced to nothing visible has not yet been lived. The humans who will live it will be changed by it in ways we can only partially predict. The engineering challenge of a Mars mission is usually framed as propulsion, life support, radiation shielding, entry, and landing. Those problems are real and difficult, but the deeper problem may be this: building a vessel and selecting a crew that can survive months inside the dark, without breaking, and arrive capable of doing the work that comes next. But step back from the vessel, the crew, the engineering problem, and ask a simpler question. What is actually out there in that dark? The honest answer is stranger than it sounds. Start with light itself. When we say space is dark, we mean dark to human eyes. And human eyes are a narrow instrument. The light your eye can detect runs from roughly 400 nanometers at the violet end to roughly 700 nanometers at the red end. Less than 1 octave. Less than a single doubling of wavelength. The full electromagnetic spectrum, from radio waves meters long to gamma rays shorter than an atomic nucleus, spans more than 60 octaves. We see less than 2% of the light that exists. Think about what that means. The rest of it is there. It passes through you. It fills the spaces between galaxies. You simply cannot see it. And the places that look darkest are not empty of it. The regions of space that appear absolutely black to human eyes are saturated with electromagnetic radiation outside the visible band. Distant galaxies have had their light stretched by billions of years of cosmic expansion. What left those galaxies as visible light has been pulled into infrared wavelengths by the time it reaches us. Invisible to the eye, but detectable by instruments designed for it. The James Webb Space Telescope observes primarily in infrared. It sees entire galaxies that are completely invisible to optical telescopes. Not faint, not reddish, completely absent to the human eye, and blazing with structure to the Webb. There is also the cosmic microwave background. It fills the entire sky in every direction. It is the afterglow of the Big Bang, radiation from the earliest era of the universe, now stretched by expansion into microwave wavelengths. You cannot see it. Your eye has no mechanism to detect it. But it is there, right now, carrying information about conditions 13.8 billion years ago, passing through every point in space, including the room you are sitting in. Radio waves from pulsars and quasars travel billions of light years through dust and gas that would stop visible light entirely. Radio telescopes on Earth detect them as clear signals. To your eyes, that direction of sky looks dark. To a radio antenna, it is loud. Human perceived darkness is partly a biology problem. Our eyes evolved to detect the wavelengths the sun produces most strongly, and the atmosphere transmits most easily. That was useful for staying alive on Earth. It is not a window onto the full universe. It is a keyhole, but the picture did not hold. Even if you could see the full electromagnetic spectrum, you would still be missing most of what is there. A perfect vacuum, the most thoroughly emptied region of space humans can conceive, is not truly empty. Quantum mechanics describes a phenomenon called quantum fluctuations. Virtual particle and antiparticle pairs appear and annihilate constantly, everywhere, including in regions perceived as absolute dark. They do not persist long enough to be detected directly, but their effects are measurable. This energy, the baseline hum of the vacuum itself, is called vacuum energy, or zero-point energy. It may be connected to dark energy, the force driving the accelerating expansion of the universe. The darkness is not still, it seethes, not with matter you could touch, not with light you could see, but with quantum activity at a level below ordinary perception. This raises a genuine question. Is darkness the absence of light, or is it our inability to perceive what is present? The answer gets more unsettling when you account for the two largest components of the universe. Dark matter makes up roughly 27% of the universe's mass and energy. It emits no light. It absorbs no light. It reflects no light at any wavelength. We cannot detect it with any optical instrument, any radio telescope, any device tuned to any band of the electromagnetic spectrum. We know it exists only from its gravitational effects. Galaxies rotate too fast for the visible matter they contain. Light bends around regions where no visible mass exists. Something is there. It interacts with ordinary matter only through gravity. It passes through you constantly. Through the Earth. Through every wall. Through every material we have ever made. Without a trace. No analogy quite captures what that means. Ghosts in fiction at least occupy space. Dark matter does not interact with the atoms in your body in any way you can feel, hear, or observe. Billions of dark matter particles stream through your body every second, through the floor you sit on, through the planet beneath that. You do not feel them. You cannot feel them. There is no sense organ for gravity operating at that scale. They leave nothing. Dark energy is roughly 68% of the universe's total content. It drives the accelerating expansion of space. It does not interact with light in any detectable way. We do not know what it is. Physics does not yet explain it. We know it exists because of what the universe is doing, not because of anything we can point at. Add it together, dark matter, 27%. Dark energy, 68%. Roughly 95% of the universe's total mass and energy content is invisible to us by any direct means. Not slightly invisible, completely invisible, at every wavelength, by every instrument we have ever built. The darkness we see is not the absence of content. It is the presence of things we cannot detect. The void is not empty. We are just not equipped to perceive what fills it. There is one more layer to this. What you experience as darkness is itself a signal from your brain. When photons hit the retina, chemical reactions trigger electrical signals that travel to the visual cortex. With no photons arriving, the cortex receives no input. But you still experience something. You experience darkness. That is not nothing. That is your brain generating a representation of absence. The darkness you see is produced by your own neural architecture. It is not the thing itself. Two people standing in identical physical conditions, zero photons reaching either eye, may experience that darkness differently. Some people are more sensitive to residual low-level signals. Some find the absence peaceful. Some find it threatening. The subjective experience varies because the brain doing the representing varies. Space looks empty. That is the first layer. But it is packed with light we cannot see, with particles we cannot feel, with quantum activity we cannot observe, and with 95% of everything in the universe that is, by its nature, fundamentally invisible to us. The darkness is both real and subjective. Real, because in many regions there are genuinely zero photons in the visible band. Subjective, because the darkness you experience is your brain's rendering of that absence, not the absence itself. And even that rendering tells only part of the story. The physics underneath the dark, the quantum field seething in every cubic centimeter of the void, the dark matter threading through every solid object, the ancient microwave radiation filling the whole sky in every direction. Those things do not wait for us to notice them. They were here before any eye existed, to fail to see them. They will be here long after. What we call darkness is mostly a limit of our instruments, and that limit goes deeper than the eye. There is a place in the universe where the word dark stops being a description and becomes a definition. Not a region of empty space, not a shadowed crater on an asteroid, not the interior of a sealed vault with every photon absorbed. Something categorically beyond all of those. A black hole is a region of space-time where gravity has become so extreme that nothing can escape. Not dust, not gas, not radiation, not light. Once anything crosses the event horizon, the boundary of no return, it cannot come back out. The gravity curves space-time so severely that every path forward, every direction a photon could travel, leads inward. There is no outward anymore. This makes black holes perfectly black. Not dark the way space is dark, where photons are simply absent because matter is sparse. For the opposite reason entirely. Space is dark because it is nearly empty. A black hole is dark because it is so full of gravity that light cannot leave at all. One is an absence. The other is a trap. They look the same from the outside. They are nothing alike in what they are. The Event Horizon Telescope gave us the first direct images of this. It is a collaboration of radio telescopes spread across the Earth, linked together to act as a single instrument the size of the planet. In 2019, that instrument produced an image of the supermassive black hole at the center of the galaxy M87, a galaxy 55 million light-years away. And then in 2022, an image of the supermassive black hole at the center of our own Milky Way. Both images showed the same thing: a bright ring of hot, glowing material orbiting at enormous speed with a dark center. That dark center is the shadow of the black hole. It is darker than anything else in the image because it is an actual void. Light falling towards it does not reflect back. Light trying to escape from near it curves inward. The ring glows. The center does not. It absorbs everything that reaches it and returns nothing. If you could approach one, the view would be unlike anything else in the universe. Looking toward it, you would see a circular hole in space. Not a dark object. A hole. The stars behind it would not be hidden exactly. They would be smeared into a ring around the edge of the void by gravitational lensing. Gravity bending their light around the black hole's perimeter, curving paths that should have continued in straight lines, compressing the entire sky behind the object into a ring of distorted starlight, wrapped around pure darkness. At the center of that ring, nothing. Not dim, not deep, absolute. That is the darkest thing we know of. And having named it, it is worth holding the contrast clearly. The darkness of interstellar space, of intergalactic voids, of asteroid craters, of every place the eye strains and finds nothing, all of that is darkness by absence. The black hole is darkness by physics. It is the only place in the universe where the question of whether any light exists at all has been answered with a hard no. Not by the sparseness of matter around it, but by the geometry of space-time itself. Now step back from the extreme and look at the real terrain between the sun and the edge of its reach. Because the question of how much light each destination actually receives is not an abstract one. It is the question every human being who leaves Earth will live inside. Start close. The International Space Station orbits at roughly 250 miles above the surface. At that altitude, the sun is unchanged from Earth's surface in terms of intensity, slightly stronger even because there is no atmosphere absorbing any of it. Earth fills much of the windows. The crew experiences 16 sunrises and 16 sunsets every single day, one every 90 minutes, because they lap the planet that quickly. The longest stretch of darkness per orbit is about 45 minutes. And even in that window, city lights glow below, visible across hundreds of miles of night. ISS astronauts do not experience true space darkness. They are close enough to home that home is still the dominant visual fact. Move outward to the moon, and the situation changes completely. The moon has no atmosphere. That single fact reshapes everything about light and dark on its surface. On Earth, the atmosphere scatters sunlight before it vanishes below the horizon, giving us twilight, dusk, a gradual softening. On the moon, none of that exists. The sun is above the horizon. Then it is below. That transition takes seconds. The sky does not dim. It does not fade. Darkness arrives the way a door closes, and it stays. Lunar night lasts approximately 14 Earth days. 2 weeks of unbroken darkness at every point on the surface outside the poles. The only sources of illumination during that period are Earthshine and starlight. Earth, seen from the moon, is about 4 times wider than the moon appears from Earth, and far more reflective. Earthshine is real, and it is brighter than moonlight on Earth, but it is still insufficient for detailed work. Precise navigation, equipment inspection, geological survey, all of it requires artificial light. The Artemis program's surface habitats will need extensive lighting systems. Rovers will need powerful headlights. There is no workaround. Lunar night is not a nuisance condition. It is a construction requirement. The full day-night cycle on the moon is roughly 29.5 Earth days. No human circadian system runs on a 29-day clock. Every lunar habitat will need to generate its own artificial day, an internal rhythm of light and dark, completely disconnected from the sky outside the window, because the sky outside gives no usable cue for any biological schedule humans are equipped to follow. Mars is warmer in one respect. The day there is 24 hours and 39 minutes, nearly indistinguishable from an Earth day. The circadian problem that makes the moon so difficult largely disappears, but the light does not. Mars receives approximately 43% of the sunlight that reaches Earth, roughly half. Midday on Mars is comparable to a heavily overcast afternoon on Earth, bright enough to see by, dim enough to require supplemental lighting for anything requiring precision. The thin Martian atmosphere does produce some twilight, a brief softening at sunrise and sunset, and Mars has two moons, Phobos and Deimos, both tiny, both irregular, both contributing essentially no useful illumination at night. Martian nights are dark. Habitats will supplement natural light not only for practical visibility, but for circadian maintenance, because at 43% of Earth's sunlight, the natural day does not fully signal the brain the way a full-strength day does. Past Mars, the numbers shift decisively. Jupiter receives about 4% of Earth's sunlight. 4%. Standing on one of Jupiter's moons, the sun would look like a very bright star, not a source of warmth or comfortable vision. A point of intense light in a black sky, bright enough to cast faint shadows, not bright enough to work by without artificial supplementation. Saturn receives about 1%. At Saturn, the sun has shrunk to something like a street light, seen from several blocks away on a clear night. You can tell which direction it is. You cannot read by it. You cannot do precision work in it without aid. Titan, Saturn's largest moon, has a thick atmosphere denser than Earth's, and that atmosphere scatters what little sunlight arrives into a permanent, uniform twilight. Even at noon on Titan, the surface receives roughly 1% of Earth's midday sunlight. It is like being outdoors on Earth an hour after sunset. You can see, colours are muted, shapes are legible. Anything requiring focus needs a light source you brought with you. That is when the pattern broke. We assume, almost automatically, that artificial lighting is a minor logistical matter. We bring lights. We turn them on. The problem is solved. But at outer planet distances, artificial light is not supplemental. It is the entire system. The sun is no longer a meaningful source of illumination for working humans. It is a navigational marker, a dim beacon, not a light source for daily life. Uranus receives about 0.27% of Earth's sunlight. Neptune about 0.11%. At those distances, the sun is roughly 200 times brighter than Earth's full moon as seen from Earth. That sounds like a lot. Earth's full moon is enough to cast soft shadows and walk by on a clear night. 200 times brighter should be substantial, but 200 times brighter than the moon is still, in absolute terms, a faint light. It is enough for emergency navigation. It is not enough for any detailed task. Any outpost in the outer solar system, approaching the Kuiper belt, the ragged boundary where the sun's influence fades, operates in a world where artificial light is not infrastructure. It is the fundamental condition of being awake. The habitat design question follows from this directly. Underground bases offer protection from radiation and extreme temperature swings. The cost is total darkness. No windows, no connection to the sky, artificial light from the moment you wake until the moment you sleep, every day. Surface habitats with windows preserve a visual link to the outside. But outside, at these distances, means a barren terrain under an eternally black sky, stars overhead with no atmospheric scatter to diffuse them, and a sun that may not even be the dominant source of visible light in the view. Some people, faced with that sky, find it extraordinary. The stars are perfectly crisp, unobstructed by any atmosphere, deeply beautiful. Others find the absent blue, the missing clouds, the unchanging black overhead oppressive in a way that compounds over time. Both responses are real. Both will be present in any crew. What we tend not to think about when we imagine carrying lights with us to the outer solar system is that we are imagining something more fundamental than a power system. We are imagining building a new relationship with day and night entirely, not modifying it, not supplementing it, replacing it from scratch. And the further out you go, the more completely that becomes true. The outer solar system does not offer a dim version of what we have on Earth. It offers something else, And learning to live inside that something else will require more than good engineering. Engineering a world to live inside. That is what the outer solar system demands. But the engineers designing those habitats, and the crews who will one day inhabit them, exist within something larger still. Something that dwarfs the distance to Neptune the way Neptune dwarfs a footstep. And to understand the darkness we have been tracing across this entire journey, we need to step outside of now altogether. Not just outside of Earth, or outside the solar system. Outside of our moment in time. The universe has a history. A long one. And that history is mostly dark. Start with something simple. When you look at the Andromeda galaxy on a clear night, you are not seeing Andromeda as it is. You are seeing it as it was 2.5 million years ago. That is how long its light has been traveling to reach your eye. The image you're receiving left Andromeda before our species existed. The most distant galaxies we can observe are farther still, over 13 billion light years away. We see them as they appeared a few 100 million years after the Big Bang. What those galaxies look like now, we cannot know. The light carrying that information has not arrived yet. Some of it will in billions of years, and some of it never will. Then the data shifted. The expansion of space is accelerating. Some galaxies are already moving away from us faster than light can cross the growing gap between us. Not moving through space faster than light. Space itself between us and them is expanding faster than light can traverse it. Their light, aimed toward us right now, will never reach us. It will travel for eternity and never close the distance. Those galaxies are beyond our cosmic horizon. They exist. They burn with stars. And we will never see a single photon from them. Not a theoretical limit. A physical one. Permanent. And over time, more galaxies will cross that horizon. The observable universe is not growing. It is shrinking. Galaxies that are visible today will eventually redshift into invisibility, their light stretched by expansion until it falls below any wavelength we could detect. In the far future, beings living in what remains of our local group will look out at a universe stripped of its distant structure. They will see far fewer galaxies. They may not even be able to tell the universe is expanding because there will be nothing distant enough left to measure against. They will inherit a darker sky than ours, and they may not know what they are missing. Our view of the cosmos is specific to now. It is ours, and it is temporary. But this is not where the darkness began. To understand how extraordinary our moment is, you have to go back. Shortly after the Big Bang, there was no darkness anywhere. The universe was a hot, dense, glowing plasma, every point in space radiating light, not scattered sources of light separated by dark gaps. Light everywhere, continuously, simultaneously. No stars, no galaxies, nothing we would recognize. Just primordial glow, so dense and so hot that photons could not travel more than a short distance before colliding with free electrons and scattering in a new direction. The universe was opaque, brilliant, and opaque. Then, about 380,000 years after the Big Bang, something changed. The universe had been expanding and cooling the whole time, and at 380,000 years, it cooled enough for electrons and protons to combine into neutral hydrogen and helium atoms. This moment has a name: recombination. It sounds technical, but the consequence was immediate and enormous. Free electrons had been the obstacle, scattering photons in every direction. When atoms formed, the electrons were captured. The obstacles cleared. Light that had been bouncing endlessly could finally travel freely across space. It streamed outward. We can still detect it today as the cosmic microwave background, the faint afterglow of that moment, stretched by billions of years of expansion into microwave wavelengths invisible to the eye. But here is what came after recombination, and what almost no one thinks about. The light departed, and then came the dark. Not a brief transitional dark, a deep, sustained, total dark that lasted hundreds of millions of years. The plasma had cooled into neutral gas. The CMB was still present, but cooling and redshifting into invisibility. There were no stars, no galaxies, just hydrogen and helium clouds drifting and slowly gravitationally collapsing in some regions. Not yet dense enough to ignite fusion, not yet hot enough to shine. The universe was full of matter, full of energy, in the form of that cooling radiation, and it produced no light. This is the cosmic dark ages, the darkest era in the history of the universe. Not dark because it was empty, dark because nothing in it was burning. That darkness lasted until approximately 200 million years after the Big Bang. Then, the first stars ignited. They were unlike anything that exists today. Massive, some of them hundreds of times the mass of our sun, burning at extraordinary temperatures, blazing with ultraviolet radiation that began to ionize the gas around them. They were brief. A star that massive burns through its fuel in a few million years, and then explodes as a supernova. But those explosions were not endings. They were beginnings. Each supernova scattered heavy elements, carbon, oxygen, iron, nitrogen, into the surrounding gas. Elements that had not existed before. Elements that would eventually become planets. Elements that would eventually become us. The universe was beginning to seed itself with everything complexity requires. Over billions of years, more stars formed from that enriched gas. Galaxies assembled. Star formation accelerated. The universe became brighter, not uniformly bright, but concentrated into brilliant regions separated by vast dark voids. And roughly 10 billion years ago, star formation reached its peak. More stars were being born per year across the universe than at any point before or since. That peak is behind us. We live in a universe past its brightest moment. Star formation has been declining for 10 billion years. The rate is still positive. Stars are still being born, but the trend is downward and it will not reverse. Over trillions of years, the available gas will be consumed or expelled. The raw material for new stars will run out. Star formation will slow to a trickle and eventually stop. The existing stars will age. The most massive ones are already gone, collapsed into black holes or neutron stars within millions of years of forming. Stars like our sun will eventually exhaust their hydrogen, swell into red giants, and shed their outer layers, leaving behind dense glowing cores called white dwarfs. Those white dwarfs will cool over trillions of years into dark, cold objects called black dwarfs. The smaller stars, the dim red ones burning at a fraction of the sun's rate, will last longest. Some will burn for trillions of years before they too run out of fuel. But they will run out. In approximately 100 trillion years, a number so large it bears its own notation, 10 to the power of 14, the last star in the universe will exhaust its fuel and go cold. After that, no new light is generated anywhere. The stellar era, the era we inhabit, will be over. What remains will be black holes, neutron stars, cooling white dwarfs becoming black dwarfs, dead planets orbiting dead stars, cold rock and ice traveling through a universe that no longer illuminates itself from within. Occasional events will still occur. A planet falling into a black hole will briefly flash with irradiation. Two white dwarfs colliding might briefly explode. But these events will grow rarer as the remnants spread further apart through continued expansion. The universe will be dark in a way it has not been since the cosmic dark ages. Darker, in fact, because now even the background glow of the CMB will have faded to nearly nothing, and the black holes will still be there. Stephen Hawking predicted that black holes are not truly permanent. Quantum effects near the event horizon, the point of no return we examined earlier, cause black holes to emit faint radiation. Extremely faint. So faint it is utterly undetectable around any black hole that exists today. But over vast timescales, this Hawking radiation carries away energy, and the black hole slowly loses mass. A black hole with the mass of our sun would take approximately 10 to the power of 67 years to fully evaporate. Write out that number and it is a 1 followed by 67 zeros. The current age of the universe is roughly 10 to the power of 10. So a solar mass black hole would last for a period longer than the current age of the universe, repeated 10 to the 57th times over. These are not durations the human mind can hold. They are only numbers, but the physics says they are real. By approximately 10 to the power of 100 years, one followed by 100 zeros, even the largest black holes will have evaporated completely. After that, the universe holds photons, neutrinos, and scattered fundamental particles spread across space so vast and so cold that the temperature is effectively zero. No energy gradients remain, no process can run, no change can occur. This is heat death. The second law of thermodynamics states that entropy, the measure of disorder and equalized energy, increases over time. Heat death is that law reaching its conclusion. Maximum entropy, nothing left to drive any event anywhere. Dark, cold, still, forever. The arc is complete. The universe began in light, brilliant, total, scalding. Then it passed through darkness, the cosmic dark ages, hundreds of millions of years of genuine night, with no star anywhere. Then it entered the bright era, the one we inhabit, where stars formed and galaxies shone, and the darkness was merely the space between living fires. And then, the light will fade again, and the darkness that follows will last not for hundreds of millions of years, but for spans so long that the current age of the universe is not even a rounding error against them. The final dark will be the longest dark. It will be, in any meaningful sense, eternal. We are in the brief, bright window. We happen to exist during the interval when the universe is lit. When you look up at a sky full of stars, you're not seeing the default state of the universe. You are seeing the exception. A warm, lit moment between two vast darks. And the light it took billions of years to produce, the light that crossed intergalactic distances to reach your eye, the light you almost certainly never think about as you glance up on a clear night, is doing something it will not always be able to do. It is arriving. Still arriving. For now. Let's come all the way back. From the end of time, from the cold and the stillness and the dark that lasts effectively forever. Back to here. Back to now. Back to a child standing in a backyard on a clear summer night, looking up. The child sees a handful of stars. Maybe a few dozen if the air is clean. The moon if it is up. The orange haze from the city bleeding across the horizon. And nothing else. That is all they have ever seen. And they do not know they are missing anything. For most of human history, night meant real darkness. Fire and candles gave small pools of light, but the sky above was always present, always full. Activity followed the sun. You knew from a young age what the actual sky looked like, because there was no alternative version competing with it. Then came gas lamps, then electric light, then entire cities that never dimmed. Enormous benefits followed. Commerce, medicine, safety, freedom from the tyranny of the sunset. No one should pretend otherwise, but something was lost. Quietly, incrementally, without anyone deciding to give it up. Today, about 80% of the world's population lives under light-polluted skies. In the United States and Europe, that figure exceeds 99%. Not most people. Virtually everyone. The glow from cities spreads for hundreds of miles in every direction, pooling together into a background brightness that never fully fades. From a major city you might see a few dozen of the brightest stars. Constellations blur. Planets are faint suggestions. And the Milky Way, that dense river of light arching across the full sky, is completely invisible. Many children raised in cities have never seen it. They have no felt sense that it exists. Space, for them, is a concept in a textbook, not something you look up and feel. There are places where the sky is still protected. Dark sky preserves, where artificial lighting is strictly controlled, and natural darkness is treated as something worth defending. Visiting one is like stepping back into a world that used to exist everywhere. Thousands of stars where you expected dozens. The Milky Way clearly defined, not a smear, but a structure, with lanes of dust and brighter concentrations, and the sense of depth that a galaxy actually has. Planets blazing, satellites crossing on schedule, meteors appearing and fading. The International Space Station, when it passes, bright enough to cast a faint shadow on the ground beneath you. People who visit these places for the first time often go quiet, not because they have nothing to say, because the words come slowly when the real sky arrives. But the severing of our relationship with the sky is not only a loss of wonder, it cuts deeper than that. Humans evolved with clear day-night cycles. Circadian rhythms, the internal biological clocks that regulate sleep, metabolism, immune response, and dozens of other functions, are tuned to that pattern. Artificial light at night tells the brain it is still daytime. The brain suppresses melatonin production accordingly. The rhythm drifts. The consequences accumulate. Insomnia, depression, elevated risk of obesity, diabetes, and some cancers. The same biology that once read the sunset as a signal to begin winding down now receives no such signal at all. Future long-duration space missions will face the same problem from a different direction. A carefully designed lighting system, blue enriched during work hours for alertness, warmer and dimmer in the evenings, completely dark during sleep, will not be a luxury. It will be a requirement. Lunar habitats, where the external day-night cycle runs on a 29.5 Earth day schedule, no human body can follow, will need to generate an entirely artificial internal rhythm. Mars habitats will need supplemental light, just to offset the psychological weight of days only 43% as bright as Earth's. Here's where the pattern becomes clear. Cities are already bubbles of light in the night. Space habitats will be bubbles of light in the cosmic dark. The shift is one of degree, not kind. We have been rehearsing for this for a century. The irony is that the rehearsal cost us the direct experience of the real thing. The darkness is not theoretical. It has been faced by individuals, and their accounts of it are the first reports back from inside. December 1968, Apollo 8. The crew was Frank Borman, Jim Lovell, and William Anders. The mission was the first to carry humans to another world, the first to place human eyes above the lunar surface. On December 24th, they became the first humans to orbit another celestial body. And when their trajectory carried them behind the moon, radio contact with Earth was lost. For about 45 minutes, they were completely alone, farther from any other human than anyone had ever been. Below them, the grey cratered surface of the moon, lit by harsh, unfiltered sunlight. Above them, darkness. Jim Lovell described looking into that darkness and feeling profoundly alone. The stars were visible as tiny points, each giving no sense of proximity or scale. They could have been nearby or infinitely far. The darkness felt infinite, like one could fall into it forever and find no bottom and meet no edge. When they came around the far side and Earth rose above the lunar horizon, a half-lit blue-white sphere against pure black, the relief was enormous. William Anders captured the image. Earthrise. A photograph that changed how humanity sees itself, not because it showed something beautiful, though it did, because it showed something small, vivid, and small, and surrounded by absolute nothing. 4 years later, in December 1972, Apollo 17 produced the blue marble, Earth fully illuminated, a sphere of blue oceans and white clouds and brown landmasses against pure black. No other objects, no other colors, Earth alone. It has been called the most reproduced photograph in history. Its power comes from the contrast. Everything vivid, everything alive, pressed against absolute darkness that surrounds it completely. But the most unsettling account came from a mission that was not supposed to be about darkness at all. April 1970. Apollo 13. An oxygen tank exploded 2 days after launch, crippling the spacecraft. The crew abandoned the command module and moved into the lunar module, the small landing craft that was never designed to carry all three of them for the full return journey. To conserve power, they shut down almost everything, including most of the lights. The spacecraft became cold and dark. For days, they drifted in that condition, rationing every watt, looking out the windows at the void, uncertain whether the improvised course corrections would actually bring them home. Lovell later wrote about what it was like to look at the darkness surrounding the ship during those days. Not frightening in the way a visible threat is frightening. Worse than that, indifferent. The darkness would be there whether they made it home or not. It registered nothing about their survival, their effort, their hope. An enemy can be fought. Indifference simply is. They made it home. Systems held. Mission Control improvised the navigation. The crew splashed down safely in the Pacific. But they came back with something that cannot be fully conveyed in mission reports. The knowledge that the darkness does not care. The machines have gone further. Voyager 1 and Voyager 2, launched in 1977, made the first close approaches to Jupiter, Saturn, Uranus, and Neptune. They returned the first clear images of Jupiter's Great Red Spot, a storm larger than Earth that had been spinning for centuries. Saturn's rings resolved into thousands of individual ringlets. Moons that had been mere points of light became worlds. Io with active volcanoes, Europa with an ice-covered ocean, Titan with its thick orange atmosphere, Triton with nitrogen geysers erupting from a surface of frozen nitrogen. And then the missions continued outward. On August 12th, 2012, Voyager 1 crossed into interstellar space, not a boundary you can see or feel, a boundary defined by where the sun's influence ends and the true interstellar medium begins. It was the first human-made object to make that crossing. It is now more than 15 billion miles from Earth, more than 160 times the distance from the Earth to the Sun. Signals traveling at the speed of light take more than 22 hours one way to reach it. Out there, the Sun is still the brightest point in the sky. But it is a point. Earth is invisible, not faint. Invisible. Indistinguishable from the background stars even with functioning cameras. Voyager carries the golden record, a phonograph disc etched with sounds and images from Earth. Music, greetings in dozens of languages, the sound of wind and rain and surf, a message in a bottle cast into the cosmic ocean. Whether or not anyone ever finds it, it is already something more than a communication attempt. It is a monument to a species that looked outward and wondered if anyone was listening. Voyager's nuclear battery loses about 4 watts of power each year. Somewhere around 2025 to 2030, it will no longer have enough power to run any of its instruments. It will fall silent. The signal will stop. And Voyager will continue drifting through the dark, alone and lightless, for longer than the entire history of civilization, repeated millions of times over. In about 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445, roughly 95 trillion miles at closest approach. Close enough to name, not close enough for gravity to capture it. Voyager will continue past. New Horizons flew past Pluto in July 2015 and sent back images of mountains made of water ice and plains of frozen nitrogen, and an atmosphere more complex than anyone predicted. At Pluto, sunlight arrives at about 0.06% of what Earth receives, roughly 300 times dimmer than a bright indoor room. Not complete darkness, but something between twilight and night. The sky above Pluto is black at noon, stars visible, shadows absolute, because there is no scattered light to fill them. In January 2019, New Horizons reached Arakoth, a Kuiper Belt object about 4 billion miles from the Sun. The most distant object any human machine has ever explored. A pristine remnant from the formation of the solar system, 4.6 billion years old, barely touched since the first dust grains clumped together in the solar nebula. It has been sitting in the dark that long. New Horizons will eventually fall silent too, another artifact swallowed by the void. The darkness is not something we will eventually face. We have been sending things into it for 50 years. We have sent people to its edge and listened to what they came back saying. Not slightly afraid, not slightly changed, marked by it in ways that took years to fully articulate. And every machine we have sent outward, every image it returned, every signal we have tracked across tens of billions of miles, has confirmed the same thing the astronaut said from behind the moon. The dark is real, it is vast, and it does not notice us at all. But we noticed it. That, so far, is the difference. And there are more reports still to come. Those reports will keep coming. But here is the question they have always been circling. The machines we sent are out there, drifting. The golden record is traveling through interstellar space with its greetings and its music and its sounds of rain. And there is no evidence, not one signal, not one anomaly, that anyone has ever noticed. That silence, has a name. Enrico Fermi, the physicist, asked the question simply at a lunch in 1950. If intelligent civilizations are common in the universe, where are they? Cities produce light pollution detectable from space. Megastructures would emit or reflect light on a scale we could measure. Communications would spread at the speed of light, propagating outward in every direction, filling the galaxy over millions of years. We have been listening for decades. We have scanned the sky in radio wavelengths, optical wavelengths, infrared. We have found nothing aimed at us, no signal we cannot explain through natural sources. The darkness is unbroken by any obvious sign of mind. There are possible explanations. One is that we are alone, or nearly so. That intelligent life is so rare in the galaxy that we may be among the first, looking out into a universe that has not yet produced another mind capable of looking back. Another is that others exist, but are simply too far away. Light from their worlds may not have reached us yet, or it may have arrived and been too faint to distinguish from background noise. A planet entirely covered in cities, lit from pole to pole, would still have its light drowned by its parent star from light years away. We can detect thousands of exoplanets now. We cannot see their surfaces. We cannot distinguish streetlights from starlight at that distance unless someone aimed a powerful, deliberate beam directly at us. The galaxy may be full of civilizations existing as isolated islands of light, each one burning in the dark, each one unaware of the others, separated not by hostility but by distance, by the finite speed of light, by the sheer scale of space that swallows unintentional signals before they cross even a fraction of the gap. Or we are truly alone, the only minds in the galaxy contemplating the darkness. If that is true, the darkness becomes something more than a physical condition. It becomes a universe full of structure, full of process, full of stars being born and dying, and empty of awareness, with only us looking out. That is not a comforting thought, but it is a profound one. We will not resolve the Fermi paradox tonight. We have not resolved it in 70 years. But it shapes how we read the silence around Voyager, around New Horizons, around every signal we have sent outward, and every ear we have turned toward the sky. The silence is real. What it means is still open. What we do know is that humans will go deeper into that silence. And when they do, the darkness will not be abstract. It will be the view from the window, unchanged, for months at a time. Researchers have studied what happens to a mind deprived of light. Flotation tanks, sometimes called isolation tanks or sensory deprivation chambers, create conditions as close as we can engineer to sensory absence. You float in body temperature salt water in a sealed room with no light and no sound. The water supports you so you feel almost no gravity. For the first 30 or 40 minutes, most people relax deeply. Muscle tension drops. Stress hormones fall. The body, no longer processing the constant flood of sensory input, settles. Then, something else starts. The brain does not go quiet when the input stops. It fills the silence with its own signal. Visual hallucinations are common, starting with geometric shapes and patterns, moving toward more complex imagery. Auditory hallucinations follow for some people. Time tracking becomes unreliable. Body position becomes uncertain, even with proprioception intact. Some people emerge from long tank sessions reporting unusual clarity or creativity. Others emerge in the early stages of panic, the brain interpreting the silence as threat. These experiments give us a preview of deep space psychology, not a perfect one. Astronauts on long missions will have crew to talk to, instruments to monitor, interior spaces to look at, tasks to perform. But the window outside will show only darkness. For months. Unchanging darkness in every direction, with no planet filling the view, no weather, no texture, no reference. The brain may tune it out, or it may fixate on it in ways that are difficult to predict and harder to correct. We will not fully know until people actually make those journeys. They will be psychological experiments as much as physical ones. This is why the selection of crew matters as much as any engineering decision. Some people are naturally more resilient under isolation. They can hold morale when cut off from everything familiar, when the darkness outside the window has not changed in 90 days, when the next communication window is hours away and any response is 20 minutes delayed. Others need constant stimulation, social variety, the reassurance of a changing environment. For those people, a deep space mission would not be a challenge. It would be a form of torment. Knowing which is which before launch is not a preference. It is a requirement. Cultural composition matters too. Individualist and community-oriented orientations handle isolation differently. International crews need diverse psychological composition, not homogeneous profiles. Strengths covering each other's weaknesses. Social dynamics shaping adaptation as much as the technology keeping the air breathable. But the reality was different. The humans most likely to adapt without strain may not be people who trained for the darkness. They may be people who grew up in it. Children born on the moon or Mars will never see Earth's blue sky directly. They will grow up under black skies. Sharp stars, no twinkling, absolute shadows. Daylight on Mars is already dim, roughly equivalent to a heavily overcast Earth afternoon. The moon has no atmosphere to scatter light or soften edges. Spaceborne children will adapt to this the way children always adapt to the conditions of their childhood. Submarine families, oil platform communities, researchers stationed at remote Antarctic bases, all of them raise children who consider their surroundings normal, who find the unfamiliar world strange when they encounter it later, not the world they grew up in. Spaceborne humans may find Earth strange. The blue sky may feel wrong to them, diffuse and hard to read, lacking the clarity they are accustomed to. Weather may feel chaotic and threatening. The planet may seem fragile compared to the predictable environment of a pressurized habitat. The stars not crisp, the shadows not sharp. Earth, not space, may be the world that requires explanation. This has a quiet parallel on Earth itself. Arctic and high-latitude cultures, the Inuit communities of northern Canada and Greenland, the populations of Scandinavia, northern Russia, Alaska, have developed strategies for living through extended darkness for thousands of years. Artificial lighting, structured social gatherings, storytelling traditions built around the long night, celebrations marking the return of the sun. Depression rates rise during dark periods, but people adapt. New practices emerge. The darkness shapes a culture rather than defeating it. Space settlements will do the same. Artificial day-night cycles built entirely around human biological need, disconnected from the outside sky. Holidays built around astronomical events, a planet's alignment, a meteor stream passage, the anniversary of a colony's founding. Shared rituals against the dark. The darkness becoming not an absence, but a context. The background against which a culture defines itself. There may even come a division. Earthborn humans who cannot adapt to space, who find the black sky oppressive and the silence unbearable. Spaceborne humans who cannot adapt to Earth, who find the atmosphere thick and the sky wrong and the noise overwhelming. Each seeing the other's world as hostile, bridged by communication and shared heritage, but genuinely separate in what they consider home. There is no full substitute for experiencing space dark yourself. Virtual reality can simulate the image. It cannot simulate the knowledge that the darkness outside the hole is real and vast and unbroken in every direction for a distance that swallows all ordinary measure. Some philosophers have framed the darkness as a mirror. Looking into the void, they argue, is also looking inward. It confronts us with our smallness, the brevity of our lives, our cosmic insignificance. Jean-Paul Sartre and Albert Camus argued that the universe provides no meaning. That meaning is something humans create, without external support, in a cosmos that supplies none. The darkness of space may be the clearest expression of that view available to us. A void onto which we project meaning because it holds none inherently. Not as a metaphor, as a literal physical fact. The darkness is not hiding something behind it. It simply is. That reading is crushing if you need the universe to care. It is liberating if you do not. If meaning must be manufactured rather than discovered, then we are not diminished by the darkness. We are defined by what we bring into it. A religious or spiritual reading reaches a different conclusion from the same facts. The darkness may be evidence of a need for something beyond the physical, or may itself be sacred, a reminder of mystery that exceeds human grasp. Both readings are responses to the same reality. The darkness does not adjudicate between them. It simply continues. This is the challenge that space exploration actually poses. Not just the engineering problem of propulsion and shielding and life support. The psychological and spiritual challenge of remaining human in a universe that is mostly dark, mostly empty, and registering nothing about our presence. If we meet that challenge, we become something new. Not a species that found the light in the darkness. A species that brought light into it. Humans once treated the ocean as an impossible barrier. A realm of monsters and dissolving certainty, where ships fell off edges and sailors went mad. We did not conquer the ocean by eliminating it. We conquered it by learning to live with it, by building the ships and training the navigators and developing the charts and accepting the sea for what it was rather than what we feared. The ocean did not become safe. We became capable. The darkness of space will not be eliminated. It will not soften as we push further into it. It will deepen, but we will become capable. Future generations who grew up under black skies, who learned to navigate by starlight and mark time by orbital mechanics, may look back at our era as the moment before the transition, when Earth was all we knew, when the darkness outside our single lit world seemed like an ending rather than an invitation. The darkness is not the end. It is where the story continues.